Could you please see my screen? Could anyone give me a feedback?
Yes.
Yes. Okay.
Works.
Okay. So I'm going to talk about impact awareness for reactive control. So basically, we would like to introduce the impact-induced state jumps into the reactive controllers, such that the impact process will be a controlled event by the controller. Basically, my presentation will have 4 parts. So first of all, we would like to address why do we care about it? Why do we need to think about impacts, and why does a robot fear it? And then we would like to think about how should we introduce the impact-induced post-impact state jumps into the state-of-the-art optimization-based controllers. And then, particularly for floating-based robots, we need to consider the standing stability and how does impact affects the standing stability. And then in the end, I would like to present some hopefully interesting experiments and the simulation results.
Yuquan, put your slides full screen.
Oh, it is not?
No, it's not.
Okay. Okay. Abder, could you see my screen?
Yeah, it's fine now. You can go
okay.
ahead.
Okay, great. Thanks for the message. Okay, so let's come back to the presentation itself. So why does a robot fear impact? Basically, the dynamic contact transitions can be problematic for the state-of-the-art humanoid robots. So let's recall these feeding examples again back in 2015. When, despite these robots are nicely designed and well controlled, the unexpected impact can lead to instantaneous momentum jump. And these jumps, unexpected jumps, can lead to instantaneous falling. And if this happens, because impact happens in a short time, the robot has no time to react to these unexpected events. Hence, the state of the art is more like this. Basically, the robot would establish contacts carefully with close to 0 contact velocities, and sometimes with the soft materials between the robot PAL and the rigid environment. So why do we need the soft materials between the robot and the rigid environment? We can have a look at what does the Journal of Impact Engineering say. So basically, in this simulation example, our conclusion is that impact is too fast to be compensated. So within this time scale, we can tell from the X label, it is actually within 1 millisecond. So if the contact velocity is up to 1 meter, 0.17 centimeter per second, for plastic materials, the peak force can reach up to 4.5 kilonewton. This is forbiddingly high. And this is in simulation. So let's have a look at what's going on with the real experiments. We didn't try 1 meter high contact velocity, but only 18 centimeter per second contact velocity. But still, we received 120 Newton peak impact force in the experiments. So over 10 iterations, we can see that the force profile are consistent. So these peak forces, how harmful are these peak forces? What are the consequences of the high forces? Basically, our conclusion is that these forces will damage hardware, for instance, the electric motors, the fragile harmonics between the gearbox and the motors, and then the impact, the contact outcome is not determined. In this case, the impact leads to the over torque of a joint, so robot immediately state immediately become infeasible. This is typical when the environment is rigid and the contact location is unknown. And when when we have underactivated robots, we also need to consider the standing stability. Otherwise, the high impact velocity would lead to instantaneous falling. In this case, the contact velocity is 0.5 meter per second. We did not put this in practice, otherwise we will for sure damage our humanoid robots. So due to these reasons, the state-of-the-art typically avoid impacts or use close to zero contact velocities. Hence, our objective is to control the impact process so that the controller knows exactly the outcome of the impact dynamics. Then, in the next section of the presentation, I will introduce you how we propose to do it and how and what are the details of our method. So to quickly recap, for hardware feasibility, we consider the limited joint velocities and limited joint torques. And for underactivated robots, such like a humanoid or a quadruped, we also need to address the standing stability. So for all these aspects, we can use this modular constraints to describe them. So basically, these joint velocity constraints, joint torque constraints, or the standing stability constraints would reflect the reality. And thanks to the modularity of the constraints, we can seamlessly integrate these aspects into our state-of-the-art reactive controllers. However, these constraints do not consider impacts explicitly. So we propose to, on top of these constraints, we constrain the post-impact state. Say after the impact, the joint velocity, for instance, needs to be below certain bounds. And we can simply rewrite the post-impact state as the pre-impact state plus the state jump. The pre-impact state is a function of the controller decision variable. For instance, the most popular choice is the joint acceleration. And our goal is to rewrite the state jump also as a function of the decision variable, for instance, joint accelerations. If we can manage this, the impact process will be a controlled process, and all impact induced state jumps will be known by the controller and will be handled consequently. Hence, the QP controller will be impact aware in the end. So let's examine how we derive the state jumps as the linear function of our controller decision variables. So let's have a look at this simple example. Basically, given a contact surface, which is the green area, we have the pre-impact velocity, which is the black arrow, and the surface normal. And then we can easily derive the post-contact velocity using the kinematic restitution. And taking the difference of these two arrows, we get the contact velocity jump. And based on this simple relation, multiplies the equivalent mass, we can conclude the impulse. Whereas, despite this approach has been adopted for many applications in one way or another, typically in the working community, this approach has well-known issues. For instance, in this example, we used a panda robot to impact a planar surface. So we only have the orthogonal contact velocity and the zero tangential contact velocity. So in this case, because we have zero tangential components, the impulse should have zero entries. Should have only non-zero entries along the contact velocity, whereas these product of the Jacobians and the inertia matrix in practice have non-zero off-diagonal elements. So in this case, for this panda robot configuration, we got these values, and this means that this multiplication would lead to a 3-element vector who have all the elements are non-zero. So this is obviously not true and not desired. So these limitations motivates people to develop more advanced impact dynamics models. For instance, back in 2000, Stelwart already discovered issues and summarized in his seminal paper. And also these issues has been recently reviewed by Featherstone. As presented by Yan Bin in the morning, he developed the graph-based approach for the planar impact models and the three-dimensional impact dynamics models. Despite the planar impact dynamics models has been successfully applied on the robots, and we have the analytical solution. The three-dimensional analytical solution is still not known. This is double verified by Michael Posa and David Remy. Especially for legged robots, the impact or collision outcomes can be ambiguous and the result may not be unique. Whereas, despite these difficulties, we can choose one's favorite impact dynamics model to write the state jump as a function of the controller decision variable. So let's have a look at a more intuitive example. For instance, the joint velocity constraint. So typically, we restrict the joint velocity below certain bounds, and the joint velocity can be rewrite as a pre-impact joint velocity, which is a function of the joint accelerations and the state jump. And we can rewrite the state jump of the joint velocity as a function of the joint acceleration, and then we can constrain the post-impact joint velocity below the predefined bounds. Typically, this is the hardware limit specified by the manufacturer. So let's have a look at 2 degrees of freedom manipulator example. So the potential field is given by an objective function. So if there is no constraints, the robot would find the optimum at the center of this potential field. If the joint velocity constraint is given, for instance, in this case, it is the box constraint, the robot would find the optimum at the red circle. Whereas if we consider the impact dynamics due to the state jumps, the new constraints would be these solid lines. So these new constraints would change the optimum from the red circle to the green circle. Despite the optimum has changed, the joint velocities will be respected despite the impact. So with the new constraints in practice, I will show later with experiments that we can achieve much higher contact velocity than the close to zero state of the art. So let's have a look at a simulated video. We documented the result in RSS 2019, and the implementation, the Python implementation is openly available on GitHub. So if we do not consider impact dynamics and the robot just collide with the wall, or some of the joints will over torque, and the robot hardware will be damaged. Whereas if we apply the approach that I presented, we can explicitly consider the state jumps and kind of safely land the impact on the unknown wall. And by the way, we always, when impact aware constraint is activated, we always assume the impact can happen at the next iteration. So that's why the proposed method is not sensitive to the impact location. And if we combine the proposed control law with admittance control, we can regulate the post-impact contact force to a predefined value. So in this case, we swiftly establish the contact and regulate the contact force to a predefined reference. And later, I will show our plots from our HRP4 robots. I mean, at the end of the presentation. And we can also optimize the robot configuration to maximize the impact force, to maximize inputs if necessary. And we can also exploit this method in manipulation tasks. For instance, if we would like to push a box with a swift motion, we can establish contact without stopping and use it in impedance controller, but rather we directly apply the impact to push the box without damaging the hardware or break the constraints. So these are the aspects we considered for fixed-based robots. What happens if we want to use the proposed approach to humanoid robots or underactivated robots? Basically, we need to address a new, we need to address the standing stability criteria. So suppose a humanoid robot is going to break a wooden piece with keratin. So initially, the robot raised a hand, and then the robot used significant contact velocity to approach the wooden piece, and then finally set the contact dynamically. And this dynamic process would lead to impulse at the pole. And then this impulse would propagate along the kinematic chain to a center of mass, as presented this morning by Professor Nanchif and Patrick. Typically, humanoid robots are joint position controlled, so the joints are kind of locked, so we can observe significant floating base velocity jump, but very minor, but relatively minor joint velocity jump. So our question now is if we move to humanoid robots, our question now is to how do we compute the centroidal momentum jump? So basically, we adopted the planar frictional impact dynamics model by Yan Bin, published in 2019, that is used in the robot betting example. And we have an open source implementation, and the interested readers are welcome to use it, test it, and report bugs if you found any. And actually we found that the running, I think thanks to the analytical solution, the running time of this model is quite fast. It's only a matter of a few microseconds. So this allows us to do something interesting, such as the least square curve fitting. So this means that if every time, if we give a contact velocity to the frictional impact dynamics model, we can compute the impulse really, really fast. So this means that if we feed the frictional impact dynamics model many contact velocities, we can approximate the following linear relations. So basically, on the left-hand side, are the outcome of the frictional impact dynamics model, which are the center of mass velocity jump. On the right-hand side, we feed in the contact velocities, and the green parameter and the blue parameters can be approximated really efficiently. So here are two examples we collected from the simulations. So basically, along the x and y axis, we can online, basically within each, within each control sampling period, we can perform such approximation thanks to the fast computation time. So with this approach, the center of mass velocity jump will be a known process to the robot controller, thanks to this gradient. A similar strategy can be applied to the ZMP, to the divergent component motion, to the center of mass velocity, and also to the angular momentum, which is very important, for instance, in the backflip simulation by Professor Nanchi. With these state jumps, we can seamlessly integrate them into the whole body QP controller. And then given these state jumps, our next question is, how do we exploit them for standing stability criteria? Well, the state of the art says basically the ZMP should stay within the support polygon. So in this example, the humanoid robot HRP4 has two coplanar contacts, and he's going to push the unknown wall impacts. So we can have a look at these experiments here. And the contact velocity we established in this case is 11 centimeter per second. And we can see that the ZMP is well bounded within the support polygon. And the robot can finish the entire control cycle without breaking anything. I would not say this experiment is very impressive because the contact velocity is not as high as we are aiming for. Basically, as I said many times, we would like the humanoid robot to behave swiftly as humans. So what we do is we exploited the capture region approach. So basically, in this case, we focus on the 0-step capture region. So basically, we adopt the linear inverted pendulum model. So this allows us to work on the center of mass velocities rather than the ZMP. And the assumption that we adopt, the biggest assumption that we adopt is that we restrict the vertical com acceleration to 0. And given these two assumptions, we can compute the feasible center of mass velocity jump given the feasible ranges that we can regulate from the sustained contacts. So for instance, this is the phase portrait of the x-axis. So we can see that within the area constrained by the red dotted curves and the red solid lines, the pink lines, the robot is stable. So no matter how much the robot is disturbed, the center of mass velocity and position can always converge back to the origin. So for instance, if we check this dark green line in the middle, if the robot is sitting, in the beginning, the center of mass is at the origin, the maximum contact velocity, center of mass velocity jump we can afford is as big as 0.3 meter per second, which is significantly high. And we are going to exploit this point in the future. I mean, in the experiments that I'm going to show. And then with slightly different controller configurations, we can have different areas, but the idea are the same. So these capture region, 0-step capture region approach has been well exploited by different researchers, by Jerry Pratt, by Sugihara, by Benjamin Stephens, and more recently exploited by Li Zhibin. Whereas all of these approaches focus on the planar contacts. The striking difference is that we are going to work on non-coplanar contacts, and we consider ourselves as the first to derive 0-step capture region for non-coplanar contacts. So here is an example. The robot is applying contact velocity, applying the impact with the right paw, and then the red arrow shows the post-impact contact center of mass velocity jump. So here I would like to use this video to visualize how much does the non-coplanar foot contacts can affect the affordable contact velocity and the post-impact com velocity jump. So this change, so here when we add the left paw as a sustained contact, we can see that immediately the blue area, which is the center of mass feasible area, increased drastically, and the light green area is the ZMP area. Both of them can increase if we have one more sustained contacts. So one more sustained contacts means that the feasible contact ranges, the resultant feasible contact ranges on the center of mass will be significantly higher than merely 2 contacts. And if we remove the left paw contact, we can see the shrink. And then if we move the location of the feet contact, we can also observe the change of these feasible areas. And consequently, these areas would affect the post-impact, the maximum feasible post-impact cone velocity jump. And thanks to the linear inverted pendulum model, we can project the feasible cone velocity area. I didn't. And the reason why the red arrow and the red arrow is the maximum post-impact cone velocity. It is found at the boundary at the feasible cone velocity area. So how do we find this maximum post-impact cone center of mass velocity? Basically, what we are doing a simple optimization problem. Basically, we would like to maximize the contact velocity along a given impact direction. And then we compute the feasible post-impact cone velocity area thanks to the projection approach. And then we apply the known impact dynamics gradient. For instance, in this example, if the Young area denotes the feasible cone velocity area, that is the capture region. The contact velocity, which is the green line along the impact direction, which is the red arrow, will be found if the post center of mass velocity reach the boundary of the capture region. So we apply this principle. If we apply this principle to different stances, we can find the affordable contact, the maximum velocity for different useful practical stances. For instance, in this case, the robot has two non-coplanar feet contact, and it is going to apply impact with the right paw, and then we can see the post-impact center of mass velocity jump is found at the boundary here. And if we have three contacts, we have a different situation. In this case, the left paw is also considered as a sustained contact. And more interestingly, the robot in this case is performing a stepping task. So there is only one sustained contact, which is the right foot. And then the left foot and the robot is stepping with the bottom surface of the left foot. And then here, from the top view, we can see the post-cone velocity jump is also found at the capture region. And then we have one more stance with the kicking task. Basically, the robot again has one sustained contact with the right foot, and then it is using the left toe to kick. And then in this case, the post-cone velocity is found at the capture region in the back. Okay, so let's move on to some experiment results. Basically, with the proposed approach, we can swiftly grabbing objects for manipulation purposes. In this case, the contact velocity is 15 centimeters per second. And the interesting thing is that the robot can swiftly lift the box and put it down. And in this case, the box is actually empty due to the limited payload of the HRP4 robot. It is actually it is only a half kilo for each end effector. And then we have another push-war experiment with significantly higher contact velocity. In this case, we set the reference to be 80 centimeters per second, and the controller, thanks to the proposed approach, can autonomously find the feasible contact velocity. In the figure here, we can see that the MP has jumped outside the support. Sorry, can I? Maybe I can replay this. Yes. So basically, on the right, we will see shortly, the MP will jump outside the support polygon, but the cone velocity on the left will be bounded. So that's why the robot did not fall despite the significant contact velocity. So here is the force profile. Basically, the orange line corresponds to the force measurement collected on the force torque sensor on the robot's wrist. And in the light green phase, we activated the impact-aware constraints. And the dark green line corresponds to the predicted impact force. And we can see that at the moment of the impact, that is indicated by the dashed black line, the measured impact force is well bounded by the by its predictions. And after the impact, we switched to admittance task. Then the reference is 15 Newton. And we can see that the force measurements converge to the predefined contact force reference. And here we also plotted the angular momentum measurements, basically along x-axis or y-axis with respect to the inertial frame. The angular momentum jump are well predicted. And these, as mentioned by other presenters, is important to exploit for standing stability purposes. And then to summarize, I would like to say that the parameters, especially the frictional parameters of the sustained contacts and also the impact, can significant influence the outcome of this impact. So basically, we would like to use this interactive graphical user interface to highlight these effects. So basically, the red arrow indicates the impact velocity, and the gray arrow indicates the post-impact cone velocity jump, and this light green area corresponds to the feasible contact velocity area. That is the capture region for non-coplanar contacts. And if we change the friction coefficient of the sustained contacts, we can see that the capture region would change accordingly, and also the impact velocity increase and the post-impact cone velocity would increase, and is always found at the boundary of the capture region. And here is another stance. We have 3 contacts, including the left pole. And if we decrease the friction coefficient, we can see the capture region decreased significantly. And if the friction coefficient of impact itself changes, we can also observe the variation of the post-impact center of mass velocity. Basically, it slides along the border of the capture region. And if the restitution coefficient changes, we can observe a similar effect. A higher restitution coefficient would lead to a smaller contact velocity. Now I presented all the experiment results, and let's draw the conclusions. Basically, the idea is that we propose to integrate this controlled state jumps into the reactive optimization-based robot controllers. So this means that we can autonomously filter the contact velocity, despite the reference velocity could be significantly high. For instance, in the experiments, we used 80 centimeter per second reference, but in the end, the robot found 34 centimeter per second is feasible and friendly. And all the hardware limits and standing stability margins are respected, and our approach is robust to impact the timing or location. And we do not need to resort to reset maps or offline trajectory generations. And in the future, we would like to exploit the 3-dimensional frictional impact dynamics model, and we would like to refine impulse propagation along the kinematics tree. And as we just noticed, The parameters, friction coefficient or coefficient of restitution, have significant effects on the impact-induced state jumps, and we need to be careful with these parameters. And we also would like to investigate the effects of the tangential impulse. So thank you very much. And if you have questions, please check our preprint or directly email me. I'm wondering that, are there any questions?
Can I ask you something?
Oh, yes, sure.
I was wondering, very nice work, and I was wondering, are you going to make use of those redundant degrees of freedom? Because you can use opposite force, you can project an opposite force at the center of mass, and in this way, you can increase your impact velocity. For example, by moving if you impact with the right arm, you can move the left arm in the opposite direction, and in this way, you will generate an opposite force at the center of mass. Have you considered it? This is one question, and another question. I think it is in my studies, the pre-impact configuration is quite important. So I didn't hear about this, how you think about this pre-impact configuration. And one final question, in your movie with the box, the whole body was shaking a little bit. I was wondering, why is this? So, sorry, 3 questions, maybe too much.
Yes, I think they are excellent questions. Hopefully I can address them one by one. Yes, I fully agree that we should exploit robot redundancy to counterbalance the predicted impacts. But we are not doing it yet. I think due to the lack of enough knowledge. Yeah, but we are going to. I think hopefully we can exploit it in the future. But for now, in terms of momentum, we are focusing on the frictional impact dynamics itself, and especially for fixed manipulators. That is to say, we would like to focus on the simplest case first, and then move on to the more sophisticated cases to exploit the momentum effects. And then for the second question, the pre-impact motion is indeed very important. Again, due to the limit of time and experience, we are considering a kind of conservative approach at the moment. As I said, we always consider, as I said, our controller is reactive. So this means that we need to always consider the next control period. So basically, this means that we always assume impact can happen at the next period. So by this assumption, we benefit from that. We do not need to consider the exact impact location. For instance, in the HRP4 experiment, we never place a robot exactly at the same position to perform impact tasks. But on the other hand, I fully agree that we cannot have good pre-impact configurations because simply within one control period, we can't do anything. But just to reduce the contact velocity to a safe level. And then for the third question, indeed, the robot is kind of shaking because in the box grabbing experiment, we did not turn on the stabilizer. I mean, we do not actively control the center of mass dynamics because basically we simply would like to check if our standing stability criteria works for these impacts or not. But in the future, maybe we can improve these experiments so that they can be more impressive.
Thank you.
Thank you.